Hello friends, if you remember in my last session, I told you Westergaard analysis of determining stresses in a rigid pavement due to wheel load. In continuation of that, we will discuss today what are the temperature stresses in a concrete pavement. And temperature stresses can be because of two reasons. One, because of daily variation in the temperature between day and night, and second is because of seasonal variation in the temperature during summer and winter. We shall consider both of these. Temperature stresses due to daily variation and temperature stresses due to seasonal variation. Let us consider first the daily variation in the slab. Let us say during daytime. During daytime, the temperature at top of the slab is more than the temperature at the bottom because of direct heat coming on the top. The top surface is hotter than the bottom surface. It is cooler. And because of this temperature gradient in the pavement slab, this will expand more than the lower fiber or the lower surface of the concrete slab. So it will be like this, that the pavement slab will try to warp in this manner, warping downward. And this warping is resisted by the support system between the slab and the base or sub-base. And therefore, when it is not free to expand, then in that case, some stresses will be, internal stresses will be set up in the slab. Because of this resistive force by the base course, tensile force will be developed at the bottom and compressive force will be developed at the top. Because of positive gradient, when the top surface is hotter than the bottom surface, that will create at the edge and at the interior of the pavement slab, top will have compressive stress and bottom will have tensile stress. At the corner, when the slab curls down, then at the corner, same situation will happen here also at the center or interior or the edge. The support system here will resist the curling of this slab, and as a result, compressive stress will be developed at the top and tensile stress will be developed at the bottom. Now during night time, the situation is completely reverse. During night time, the top surface of the slab is cooler and the bottom surface is warmer. And therefore, this slab will curl upward in X and Y directions. X and Y directions. Now here again, by the same philosophy, by the same principle, that when this fiber expands, it will be resisted by the support provided by the base or sub-base, and therefore it will not be permitted to expand. So instead of tension, it will be now compression at the bottom, and tension will occur at the top of the slab. Now here at the corner, when they curl up, they basically leave the base. So they start hanging in space, and the weight of the slab will resist this curling upward curling. And therefore, here it will be tensile and compression at the bottom. So during daytime, you have this situation when compression is at the top, at the interior and edge, also at the corner. And tension is at the interior, edge and the corner. And during night time, it is tension here, compression here, tension here, compression here. Now let us see how do we calculate these stresses, warping stresses in a slab. Let us take the thickness of the slab H. Let us say the slab thickness is H, and this is the neutral axis. Above this you have a positive temperature, and below this you have the negative temperature. It can be reverse also. It can be negative, it can be positive. Now because of this temperature, there will be some strain in the slab, and that strain will depend upon this thickness as well as the E value of the concrete. Now this will be equal to alpha into T by 2. This is temperature T by 2. T is the temperature gradient, difference between the top and bottom surface. Alpha here is the coefficient of expansion, thermal expansion of concrete. So alpha into T by 2 will be the expansion of the fiber, top surface, expansion of the bottom surface. Now if you assume that the slab is infinite slab, then this strain in x direction will be equal to stress upon E minus mu into stress in y direction upon E. And similarly, the strain in y direction will be sigma y upon E minus mu into sigma x upon E. This is a strain value in x direction, y direction. This is the stress generated in the slab in x direction, in y direction, and mu is the Poisson ratio of the concrete. E is the modulus of elasticity of the concrete. Now, just to solve these equations, suppose you assume that this slab expands only in x direction. As a case 1, let us say it expands only in x direction. Therefore, this y is 0. This value is 0. And when you put this value is 0, this will be sigma y is equal to mu into sigma x, or you can say sigma x is 1 upon mu into sigma y. Put this value here and find out what is the value of x. So in that case this will be sigma x will be equal to E into epsilon x upon 1 minus mu square. And I told you this epsilon x is alpha into T by 2, and therefore this will be equal to E into alpha into T upon 2 into 1 minus mu square. That is sigma x in the first case. In the second case, we assume that it expands only in y direction and make this 0. Make this 0. So when you put it 0, then this sigma x will be equal to mu times sigma y. Put that value here and again just solve it. You get sigma x is now mu into E alpha T upon 2 into 1 minus mu square. Now when the slab bends in x and y direction, in both directions x and y, then these must be superimposed. Considering that it is infinite in both directions, sigma x will be E alpha T upon 2 into 1 minus mu square plus mu into E alpha T upon 2 1 minus mu square. That is just summing these two terms. That is the stress generated in the slab in x direction. But actually the slab is not infinite. Slab is finite in both directions, x and y, and therefore these must be corrected by some factor. And that factor let us call Cx in x direction and Cy in y direction. So for a finite slab, the sigma x will be equal to Cx into E alpha t upon 2 into 1 minus mu square plus mu into Cy E alpha t upon 2 into 1 minus mu square. Or it can be E alpha t upon 2 into 1 minus mu square into Cx plus mu into Cy. Now these are the coefficients. These are called Bradbury coefficient, after the name of the person who basically developed chart. And these coefficient depends upon two parameters. One is the length of the slab in x direction, in y direction, and the radius of relative stiffness. Means it depends upon Lx upon L and Ly upon L. And I defined this radius of relative stiffness in my last session when we were discussing load stresses in a concrete pavement because of wheel load. Radius of relative stiffness. And based on these values, Bradbury created a chart to determine the values of these coefficients Cx and Cy. That is like this. This is Lx upon L or Ly upon L, and this is Cx or Cy. If you want to find out Cx, take Lx upon L, and this is something like this. So you can find out values of Cx and Cy, Lx length of the slab in x direction and in y direction. Now this is the stress in the interior region of a slab. At edges, this stress will be either in x direction or in y direction. I mean higher stress will be either in x direction or in y direction, and therefore you can, let us put it here as I because of temperature. Stress in interior region because of temperature rather than saying sigma x, and S edge because of temperature is E alpha t upon 2 into 1 minus mu square into Cx or Cy, whichever is greater. So stress can be either in x direction or in y direction depending upon the value of Cx or Cy. And at the corner stress SC because of temperature is given by this equation, E alpha t upon 3 1 minus mu square root of A upon L. A here is the radius of loaded area and L as usual is the radius of relative stiffness. So these are the stresses at the interior, at the edge and the corner because of temperature gradient in the concrete pavement. Now let me take the same example which we considered earlier in my first session. How do we calculate temperature stresses? Now the example was like this. There is a concrete pavement with K value 2.7 kg per centimeter square. Thickness of the slab is 25 centimeter. A is 15 centimeter. The wheel load, we don't need wheel load here, 4000 kg. E of concrete is 3 into 10 to the power 5 kg per centimeter square. mu is 0.15, and with these values we calculated the stresses in the pavement due to wheel load. Now here we want to find out what the temperature stress is, and therefore you need temperature gradient. Let us say temperature gradient is 0.6 degrees centigrade per centimeter of the slab thickness. That depends upon the location of the area, region, climatic conditions. So this will be 0.6 into 25, that is 15 degrees centigrade. And alpha of the concrete is generally 10 into 10 to the power minus 6 per degree centigrade. So calculate what are the stresses because of temperature. In addition to these parameters, you need L, X and Ly. Let us say the size of the slab in X direction, that is your contraction joints, expansion joint, is 5 meter, and in Y direction it is equal to lane width 3.5 meter. Now you calculate what is L first. Again, you recall our first session, we calculated L, that is EH cube upon 12K into 1 minus mu square power 1 by 4, and this is 110.3 centimeter. This we calculated in our last session. Lx upon L is now 500 divided by 110.3. This is 4.53, and Ly upon L is 350 upon 110. This is 3.17. Enter the Bradbury chart corresponding to 3.17 and 4.53. What is the coefficient Cx? Cx is 0.73, and this Cy is 0.16. Put all these values here in this equation. E 3 in 10 power 5, alpha 10 in 10 power minus 6, T 15, 2 mu is 0.15, Cx is now 0.73, mu 0.15 and Cy 0.16. You get the stress in the interior region as 17.35 kg per centimeter square. Similarly, at the edge, you know all these parameters because Cx is now larger than Cy. So this equation is now E alpha T into Cx upon 2 into 1 minus mu square, and that makes this stress is 16.425 kg per centimeter square. This A is 15 centimeter given, and remaining parameters you know. So this will be around 4.70 kg per centimeter square. You can note here that this stress is comparatively very low as compared to interior stress and edge stress. That is how we calculate stresses because of temperature gradient, that is daily variation in the temperature. Second type of temperature variation is seasonal variation during summer and during winter. And here also during summer the slab will expand, but here the expansion is in the full length of the slab, and this expansion is resisted by the frictional force between the slab and the foundation or the base course, and that is why they are called frictional stresses, because these stresses are because of friction between slab and the base. And this movement, if this movement is free, there will be no stress in the slab, but this movement is resisted by the frictional force between the slab and the base course. And if you consider, let us say if you consider half of the slab length, then this force develops like this. This force develops maximum here at a distance of x. Initially at the center of the slab, because it is basically resisting from both sides, that is the center of the slab, there is no frictional force. It slowly develops and resists the movement, and this x is 1000 upon delta t. Delta T here is change in temperature, and this is in Fahrenheit here in this equation, and X is in inch. That should be very carefully noted, that X is in inch and this delta T is in Fahrenheit. So in our case, when we say the temperature change is 15 degrees centigrade, if delta T is 15 degrees centigrade, 15 degrees centigrade will be approximately 60 degree Fahrenheit. So 60 degree Fahrenheit. So 1000 upon 60, so 17 inch. So this X will be 17 inch. 17 inch basically means around 45 centimeter. So maximum frictional stress will develop, or frictional force will develop at 45 centimeter from the center of the. Now this can be calculated by putting the total frictional force equal to the stress work done. So frictional force, let us say for slab width of the slab is B. So what is, and the length of the slab is L and height is H. So as I told you, only half of the length is mobilized in one direction, and therefore if gamma C is the density of the concrete multiplied by B multiplied by H multiplied by L by 2 multiplied by frictional force. Friction between the slab and the base. Now here you should take care of dimensions. This is in kg per meter cube generally. So B, that is the width, is in meter. H we generally express in centimeter, and therefore it should be divided by 100. L is in meter, and that is the friction between two, that is generally 1 to 1.5. Normally we take value of 1.5, but depends upon the condition at the base. This should be equal to tensile force or compressive force, and that will be equal to stress multiplied by area, that is H into B. This is generally in kg per centimeter square, and therefore this should be converted into centimeters. So this must be multiplied here by 100. And this equation gives you SF is equal to gamma C into L into F upon 20,000. 20,000. So again, gamma C, that is concrete density, generally 2400 kg per meter cube. L you can take, let us say 5 meter again in our example problem. F, let us say you assume F to be 1.2. So you can find out what is the amount of these frictional stresses. This will be approximately 0.72 kg per centimeter square. Taking this as 2400, L 5 meter, F 1.2, this is around 0.72. So you can see here it is very, very negligible. So now because of temperature, there are three conditions: during daytime, during night time, and during season, winter. So you can create a matrix of the stresses in a concrete pavement because of temperature. And this matrix will help you to find out what are the critical conditions for design. So if you take, let us say, position in the slab and location. So position is, say, interior, edge and corner, and location for each is top and bottom. So now you can prepare this kind of matrix. What is the kind of stress developed in the concrete pavement because of warping during daytime, nighttime, frictional force during summer and winter? So interior loading, when it is, you can add one more column here for wheel load. So for this, you get compression at top because of wheel and tension at the bottom. This I explained to you in my last session. So this is compression tension and this is tension and compression at the corner. Warping stresses during daytime is CT, CT and CT. Compression at top and tension at bottom. During night time, this is reverse TC, TC and TC. Now frictional force, frictional resistance or frictional stress is during summer is at top it is compressive, at bottom also it is compressive because it is a complete expansion or contraction of the slab. And this is compression, and during winter it will be tensile force. And corners doesn't have any friction and therefore this force due to seasonal variation is not experienced by the corners. Now here you can see what is the critical conditions. Critical condition, because concrete is always weak in tension and therefore we should consider what are the critical conditions for tensile stress. Critical condition is here T, T and T. One condition. Tensile force because of wheel load at the bottom, tensile force because of warping during daytime, and tensile force because of frictional resistance in the winter season. And similarly, this one. This is also a critical condition. And third condition is this one. Tensile force because of wheel load and tensile force because of warping during night time. Frictional force is not here. So we evaluate these three conditions and take the worst one. That is how you design the concrete pavement for temperature stresses. So friends, thank you very much for watching this video. If you have any question, you can write in the comment box.